Morning everyone. So we're going to take a look at our last main section in this energy option. We actually started a little bit of this in section C4, which was introducing to you solar energy as a useful energy source. Pretty much we've been saying the sun's energy here is our ultimate source of energy. It could have been plants millions of years ago undergoing photosynthesis. They ended up producing high energy sugars for their own daily functions. Since then, the plants have long died off. They've been buried under layers and layers, either of sand or ocean water, under high temperatures, high pressures, and a lot of years as well. Ends up forming our sort of crude oil deposits, and we ended up transitioning over to talking about fossil fuels in that sense. For today's lesson here, we're coming back to the notion of solar energy. We know for plants themselves, they have organelles in their plant cells that have the structure itself is called a chloroplast. Inside the chloroplast here is a green chlorophyll molecule. Remember, the chemical feature that allows chlorophyll to actually absorb visible light is that notion of conjugation, the notion of having alternating double bond, single bond, double bond. The longer and more extensive the conjugation, the higher the wavelength, the less energy that's needed to excite those pi electrons up into that pi star. And remember, in this case here, chlorophyll, it appears to us green, not because it's absorbing green, but it's because it's absorbing the opposite of green. It's letting green as a complementary color transmit through. So what we're going to do in this lesson here is we're going to talk about semiconductors in general. We're going to talk about how can we design things to actually mimic what those chloroplasts and chlorophyll molecules do in plant cells, and how can we actually utilize that, also absorbs the sun's energy, and to convert it into a more useful form, let's say electricity that we can more easily store, more easily send long distances. Obviously, every time there's a transformation, I'm always fighting a losing battle. I'm always lose energy every time I interconvert from one form to the other. That's due to the second law of thermodynamics, which basically says heat is always going to be dissipating. We're always going to have less that's available free energy for useful work. So if we can minimize the number of transformations one to the other, all the better. So this first part here, we're just going to introduce what is a semiconductor. We're going to compare it with what we know about metals. So on this slide here, we do introduce that terminology, semiconductors. Conductor, we're talking about being able to conduct electricity. So for conductivity, we need charges, and we need charges to be able to move. So for example, compare an ionic compound. Ionic compounds do definitely have metals and nonmetals. Because of the electron transfer, we definitely have a lot of charges. However, in the solid state here, those ionic bonds here keep the structure in a lattice. Our charges aren't able to actually swim through the bulk material, so therefore the ionic compound as solid is not conductive. However, if we take that solid, if we melt it at high temperatures, or even if it dissolves in water, we then show off all those cations and anions that would have made up our ionic compound. And given in that state, because the charges can end up moving around, in fact, the more charges, even the more conductive it's going to get. So ionic compounds are definitely conductive in the liquid, molten state, or in the aqueous, dissolved state. We saw in chapter 4, metals also conduct for a similar reason. They have charges that can move. Metals are also solid, so it's like having metal, 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 metal. All the centers themselves are sort of stapled in place. But if you recall, metals generally are on the left side of the periodic table. We know they have a low Z effective, so they relatively have the largest radii on the row. Because they have such a big radius, it means that their ionization energy, relatively speaking, is low, as well as their electron negativity and electron affinity is also low. They don't really have a good ability to tug of war the electrons back after being bumped and losing that electron, and they don't really want to gain the electron. They don't really want to become negative charge. That's because given the big radius that it has, it can't actually add too much stability as a nonmetal would. In that situation, the electrons feel really unloved. We talk about them as delocalized electrons. It's like having a sea of electrons, like a pool of electrons. So although the metal nuclei, the positive centers are stuck in place, the electrons, it's really easy to bump off one from the other, and it just very quickly swims through the material. The electrons are my charged particles because they can swim through the entire material. We have what's called non-directional bonding. In chapter 4, that gave rise to, when you take a hammer to it and you sort of flatten it out, it then it's very malleable here. The layers can slide into each other layers without really breaking any bonds, as well as the ductility of it. So we're going to contrast. So those are conductors for metals. Non-metals typically are insulators, or they're very poor conductors. We know non-metals typically they're tinier atoms. They form covalent bonds. There's no electron transfer, so there's not a lot in terms of charges. And even if you manage to dissolve in water, when those molecules, we call those molecular solutions, when those molecules are in solution, they're still neutral. Semiconductors here, we're specifically looking at our sort of metalloid section. They have part of the properties of metals, part of the properties of non-metals. Specifically, we're going to look at silicon, and we're going to look at things that we can treat to silicon to make it even more conductive than it actually is. So back to this slide here. So we're going to introduce what's called the photovoltaic. The photo refers to referencing light energy and converting it over to voltaic, which is like an electrochemical cell. So converting light over into electrical energy. It uses semiconductors in place of the photosynthesis that plants do. So here's a picture here. Let's start off here with our insulators like nonmetals. We introduced to you here, imagine there's a big energy axis going up and down here. There's what's called here the valence band. This is where the electrons are in the lowest energy state. If I am able to absorb a bunch of energy, I can promote some of these electrons up into what's called the conduction band. The conduction band would be those charges that can move freely, but in this case here, being an insulator, the gap between a valence and the conduction band here is significantly large. It's not normal for a non-metal insulator here to promote a ton of these electrons up here to have enough charges that can move around to be conductive. Compare that to the opposite extreme with a conductor. For a conductor like a metal, the valence band where the electrons are typically stored up, and you notice the conduction band here is neck and neck with it. It's really close to it. So it doesn't require that much of a gap. It's really easy to promote the electrons from the lower layer to the upper layer. Once the electrons get into that conduction band, say they get delocalized, say they start moving around, they're definitely going to be conductive. On this picture here, we see a semiconductor sort of midway. It's not as conductive as a metal is. There is still some sort of band gap, but it's not as big as the band gap on the insulator side. So remember, basically what we're comparing here is we're comparing electrons would start off in the valence band and how much energy it would need to promote it up the band gap to jump it up into the conduction band. The more electrons and charged particles I can get in the conduction band, the more conductive it's going to be. So let's specifically look at these two features here. We're going to look at sort of metal conduction, and then we're going to use that to compare against our silicon semiconductor conduction. So for metals, low ionization, silicon, medium ionization, whereas for something like non-metals, really high ionization energy, that band gap here is humongous. So in metals here, we talked about having delocalized electrons. It is, at the end of the day, a Coulomb attraction, so KQ over R squared between different charged particles. The positive centers themselves are all locked down, but because we're relatively the largest radii in a row, we have low Z effective, the electrons that were on average supposed to be around every center, the electrons can swim through the bulk material. So a metallic bond is the attraction between the positive nuclei and these electrons that are swimming through. Because I have charges that can move through the material, we know definitely it's going to be conductive. However, if you temperature treat this metal here, in this case here, if I increase the temperature of the metal, the ions themselves, these positive nuclei, they tend to vibrate a little bit more. And in that sense as these electrons C model, these delocalized electrons try to swim past it, they're going to run into the ions a lot more. That increased vibration here will cause more friction. It'll make it harder for electrons to transfer through. So in general, the conductivity decreases as you increase the temperature. This is not so with semiconductors, however. For a semiconductor here, that was that middle part of the diagram, we saw we had electrons in the valence band. We saw that the band gap wasn't that huge. What's going to happen here is, starting off with a semiconductor, there is still band gap. So there aren't too many electrons at the really beginning in this high conduction band here. So there's not enough energy to promote these electrons. However, as I then increase the temperature, I'm giving the electrons a little bit more energy. The electrons more of them can jump this band gap here. Because more of them are able to get into this conduction band, I would imagine that the conductivity actually increases. So in the case of metals, because of that increased vibration, increased resistance, we expect the conductivity to drop. Whereas for semiconductors, generally speaking, the hotter it is, it's actually able to promote more electrons into that conduction band, and more of it can actually carry my current. So that's just silicon by itself. We can actually dope the silicon. We can add specific chemicals to actually even more improve this conductivity, this conduction effect that we want. In terms of doping of semiconductors here, we are going to specifically look at silicon. So this one here is our metalloid. It's sort of part properties between metals and non-metals. What we're going to do, silicon itself is group number 14, or it has 4 valence electrons if you ignore those 10 d electrons. For doping, what we're going to do here is we're going to add really small proportions. I don't need a lot, but I'm going to add a few proportions of chemicals that have 3 valence electrons, so 1 less than silicon, or group 15, they have 5 valence electrons, 1 more than silicon. Again, we don't need a lot. However, when I actually engineer this doping here, I do want some of these rare dopants, these chemicals I'm adding, to be interspersed through the lattice. So we're going to start off here. Let's dope the silicon. Silicon by itself was already a semiconductor. How does doping actually improve the number of charges that I have and actually improving the conductivity overall? We're going to start off with adding group 15, so adding things like nitrogen, like phosphorus, to the silicon. Again, we don't need a lot of them. These ones here have 5 valence electrons, meaning they have 1 extra electron as compared to silicon. So this one here is just pure silicon, so silicon, silicon, silicon. Every one has an equivalent of 4 valence electrons. You'll notice that as a metalloid here, it actually has a full octet. That's what it wanted. And now, upon adding these dopants, we now have, instead of it just being pure silicon, we've swapped out some of these here. In this case, they swapped it out with group 15, like phosphorus. Phosphorus here actually has 5 valence electron as compared to silicon, which has 4, which means we have added electron, which means that, oh, we actually have a little bit over an octet. We're not talking about expanded octet here or anything, but we're just saying amidst this big silicon lattice, which everyone had a full octet, we happen to have the odd places that have extra phosphoruses, extra electrons. And now that these group 15 elements here have that 1 extra electron, we have these electrons that have to go somewhere. Having that net excess of electrons, we now have even more charges, especially as I heat things up a bit. We have more electrons that can grab the energy to jump over into the conduction band. Because that promotion is a little bit easier, it also increases the conductivity. So basically, the more I dope it, the more free electrons that I have, and those electrons can also be promoted up into the conduction band. We refer to these as N-type semiconductor because the charge carrier we're talking about is a negative electron. Let's contrast that with the opposite dopant here. For the opposite dopant here, we have a P-type semiconductor. Again, starting off with just pure silicon here, everything has 4 valence electrons. What we're going to do is we're going to add in a group 13 or group 3 element. In this case here, we add boron. Boron only has 3 out of the 4 valence electrons that silicon has. So what's happening here is we're actually missing an electron. So although most of them have 4 valence electron, every now and then we run into a boron that only has 3 out of the 4 valence electron. There's a gap missing. We refer to this as also a charge carrier. This one here is a hole. Having a lack of electrons, it's like having a net positive charge. You can think of losing an electron as a gain of a positive charge. So having this lack of electrons relative to what we have around also gives us extra charge carriers. Those extra charge carriers, we'll call them holes. They can also allow other electrons to freely flow into them because electrons can actually naturally move into them. The holes themselves, let's say this electron over here moves to the left, that hole there ends up moving. The positive hole itself can be thought of as a charge carrier that can also move. Because it's a positively charged carrier that's actually going to do our conductivity for us, we call that a P-type semiconductor. And here's the last thing that we have to do. We have doped some of them with group 15, N-type. We doped some of them with group 13, which is a P-type. Now what we're going to do is we're going to place a P and an N-type semiconductor in close vicinity. So here we have it here. The N-type semiconductor, having a lot of group 15 elements, having that net excessive electrons, right beside a P-type semiconductor here that has a net loss of electrons, so a bunch of holes. What's going to happen here is the second that you can connect them together, when they're in close contact, the electrons will naturally, from the N-type semiconductor, want to fill up some of those holes. The holes will have a net migration up to the top. That happens naturally just for, well, negative likes positive. The electrons want to go to the side which has more positives. The holes here, because the electrons are going the opposite way, it's like the holes actually go in the opposite direction. This happens for a little while here, and then eventually we're going to build up a net charge. So although the electrons had a desire to go to the other side, as those electrons start lining up on the other side, we're actually going to build up a negative charge on this close side of the P-type semiconductor. As those holes here net migrated over to the top, we end up having a lot of positives on the top there. This creates what's called a depletion layer. There's a charge buildup. If you've done your physics here, you know there's an electric field that's set up between positive and negative. Once this depletion layer is set up, it doesn't take that long. I still will have net holes for the P-type semiconductor. Those are positive, but they're going to less and less want to cross over this gap here because the other side has become built up positive. Similarly, for the electrons here, while the electrons might have a preference to go to their positive side here, they don't really want to jump the gap anymore because the other gap has a net built up of negative charge here. Negative is repelled away by negative. So this natural depletion layer forces basically a separation of charges. After we form this depletion layer, no extra charges will build up there. No extra charges can move. We're going to actually utilize this feature then using a photovoltaic here. For a photovoltaic, we had set up this depletion layer. We put the N-type and P-type semiconductor in close vicinity. What we're going to do is we're going to either take the electrons that we already have, or we're going to send in the light energy. That's the photo part. That light energy here will promote yet more of these electrons up into that conduction band. They could be the excess electrons that the dopants bring. It could be just the silicon itself. We're going to get fresh electrons because I'm going to be building up electrons based on this added promotion here. These electrons also cannot jump through the depletion layer. What I'm going to do instead is I'm going to carry on a wire. This is an external circuit here. This is like that wiring we've done in redox chemistry here. And we basically allow it to go around a detour here as the electrons flow in one direction. That's actually going to provide us a direct current. Because the electrons are routed through this external circuit, we can taper off the electrical energy off on the right-hand side here. So we rely on this natural depletion layer. We give it a detour that the electrons can still get around from N-type to the P-type semiconductor, and we've been able to harness the electrical energy that was converted from the light energy. In fact, solar panels in our next lesson here is going to be just a large array of a bunch of these P and N-type semiconductors. We're going to be shining just natural sunlight or concentrated sunlight or other light sources here. We're going to be promoting extra electrons on the N-type semiconductor. We're going to hook it up so that we have an external circuit. As electrons then flow through, we converted the light energy over into electrical energy, very similar to how plants have done photosynthesis. They converted light energy over into sort of sugars and high energy molecules. We're actually going to, in the next lesson, look at how the solar energy can actually be converted into electrical energy using this sort of design. So let's have a look at our textbook section for this one. Okay, so this here is the textbook section. It is technically C8. This is the higher level stuff here, building on to the C4 solar energy section that we did earlier. Let's have another look at these semiconductors. Again, the main semiconductor for us here is going to be silicon. You can make a note to yourself here. Silicon here is actually a metalloid. It has some properties of metals, some properties of non-metals. In the olden days, we used to call it a semi-metal because they're sort of intermediary between metals and non-metals. Silicon by itself has a lower conductivity than metals. If you remember on the slides here, we had what was called a valence band. That's where the electrons are typically showing up. We have a conduction band at the top. Being a semi-metal or being a metalloid, there is somewhat of an energy gap here. We refer to that there as a band gap. But it's not as intense as the insulators. It's not impossible to promote electrons up from the valence band up into the conduction band, but definitely here, there's not a lot at our everyday temperatures. What we're going to do here is we're going to be able to increase the temperature here. As I increase the temperature, the thermal energy actually allows more electrons to have enough energy. The electrons were all on the bottom here. Now that I've heated it up, these electrons can actually jump up to the conduction band more. The more charges I have in the conduction band, the more conductive we expect it to be. Let's compare it with metals again. Metals, we talked about here, metals themselves have delocalized electrons. That's what metallic bonding is. At first, the delocalization was this electron C. The electrons can flow really freely around a bunch of positive nuclei here. The electrons had no trouble traveling around the bulk material. I need charges that can move for conductivity. The more charges and the easier the motion, the more conductive. However, for metals, when we heat metals, first thing is we're not going to have a net excess of free electrons. The electrons were already free to begin with. And in fact, the opposite is true. Because we have increased vibration, that increased collisions with the neighboring molecules here will actually cause more resistance and will actually make it harder for it to conduct. So that's one difference that we have between semiconductors and metals there. Not only are metals here, the band gap here is a lot tinier. When we increase temperature, we actually have a decrease generally for conductivity. For silicon by itself, without the doping here, Silicon by itself is not a good conductor because all the electrons here, if you look at having 4 valence electrons, it's like having sp3 hybridization. Everything is sort of locked away. However, as I mentioned here, as we then increase the temperature here, we allow some of these valence electrons to jump up into the conduction band itself. It frees the electrons from otherwise covalent bonds, and it's those electrons that can move through the net material. We talked about definitely it could be electrons that can move. So, for example, electrons have a negative charge. This ended up being our N-type dopants, N-type semiconductors. If I had a net loss of electrons, we can actually call it a net positive charge. We can actually look at, it's a positive hole that's actually moving around. In reality, it's actually electrons moving in the opposite direction. We still are overall neutral, so we still need to have positive equal negative. So at any given time, the number of positive holes always needs to match up to the number of negative electrons. Right? So that there's just your plain old semiconductor. We call it an intrinsic semiconductor because it already has a little bit of capacity. Sometimes if you just heat up just pure silicon, you can promote enough electrons to up into the conduction band. A lot better, however, is if we start adding these dopants. So these dopants here, as I mentioned, we're adding chemicals that are similar in size. So silicon here is row number 3. We're going to add maybe the phosphorus, maybe the boron. Boron is actually one row lower, but similar in size here. But looking at the group number here, if I add something that has an extra electron, as opposed to silicon's 4 valence electrons, say group 15 here, actually you can make a note to yourself, these have 5 valence electrons. These guys here will have a net extra electron. Again, you don't need a ton of them. We want to have small concentration. However, we do want to make sure they're really well spread out through the entire semiconductor here. That extra electron, every now and then when I run into phosphorus, just gives me more charges that can be promoted into that conduction band. If I, in contrast here, embed some borons in there, boron here would be a group 13 element. This one here only has 3 valence electrons. And therefore, we're actually having a net loss of electrons. Lacking that 1 electron, you can say this one here actually has 1 positively charged hole, 1 positively charged carrier. And in that case there, as electrons try to naturally fill in that hole there, they're always going to be leaving behind another positive charge. In reality, it's electrons that are jumping to fill in the holes, but you can also picture it as a positive hole is actually moving around, sort of the opposite direction as what the electrons themselves are naturally doing. We then couple these two designs together. So the N-type, which uses electrons as charge carriers, P-type as positive charge carriers, and we actually design it a photovoltaic by putting an N-type and P-type together. We refer to this one here as a P-N junction. If you imagine here, just on our PowerPoint slides, we showed this as well. An N-type semiconductor has a net excess of electrons. Naturally, the second that you connect them together, these electrons will want to migrate over to the other side because there's a bunch of holes on the side here. In contrast here, because the P-type semiconductors here have a net of positive charges, lacking electrons, it's like thinking about positive charges actually wanting to go to the other side to sort of, because the electrons are actually migrating over, it's like the positive charges go to the other direction. We naturally create this junction here. The name for this junction here is called the depletion layer. Once this depletion layer is built up, that charge excess will end up building up. This side of the depletion layer will be very negative because all the electrons that jumped over there. The other side will be very positive. And once that depletion layer is set up, the positive charges here would otherwise want to go to the N-type will face an electric field here. The electric field actually says positive charges should go in that direction. The positives don't naturally want to go past this way. So once that charge is built up, the depletion layer here actually has no overall transfer of electrons. And now what we're going to do, we'll do this more on the next lesson as well. We're going to then apply solar energy. We're going to still create more electrons, create more holes and whatnot. They can't jump the gap. That depletion layer is forcing them to stick around. But what's happening here is if I build up those electrons, if I put in solar energy by promoting some of those electrons up into the conduction band, I provide a detour. The electrons can actually move around this way. And basically, this is going to be DC, so it's going to be direct current. Whenever I have charges flowing in one direction, here's where I can actually taper my devices here. Just before we actually go more to that actual photovoltaic, actual solar panel design, we actually introduced 2 other really common circuit components. So in this case here, we have a component called the diode. A diode, they say it's a really simple semiconductor device. A diode's function is just to allow the current to flow in one direction. So in this case here, I know by providing a detour, I'm sort of letting the electrons naturally flow in one direction to the other direction. If this one here, instead of actually a battery, if I put this as a diode, and the diode has the negative side here and the positive side here, the electrons that are trying to travel upwards here, they may not necessarily want to hit the negative that way. So if I had the diode with the negative end in the wrong direction, even though I am providing this detour, none of those electrons will want to go to the negative side of the diode. However, if I then flip that battery around, it's not actually a battery, but if I flip the positive side and the negative side around, if I actually put the diode in the correct orientation, I have the positive side here, then that detour here becomes even more feasible because the electrons want to go to the positive side of the diode and the negative side wants to leave and it wants to go back to the other side here. So you see that if I put the diode in the wrong direction, it keeps the electrons put, they're just going to stay there. If I flip the diode around, it's a one-way gate, and basically if I have the diode in the correct orientation, it actually lets the charges go in one direction. So that one there is called the diode. We can even couple a couple diodes together and actually create what's called a rectifier. A rectifier here is one easy way to convert AC, alternating current, and DC we already saw was direct current. Basically, if I look at our electrical generation here in power plants, things like that, what we actually create out of our wall sockets is actually AC current. If you've done this in physics already, we basically we play around with changes in magnetic fields to actually create current. Unfortunately, the voltage that we're getting from the alternating current here, it's almost like having, let's say this is the wiring in your house, it's almost like having a imaginary little helper here, and this helper here is just, its job is just to hold on to this, what would otherwise be a battery, and constantly flip this back and forth. In Canada here, our frequency here is about maybe 60 hertz or so, sometimes 120 as well, but 60 hertz, it's like we have some imaginary figure. Their job is just every second, they're going to flip this back and forth, positive, negative, just to allow for that change in magnetic field. The voltage that I actually get off of there, voltage over time, we're actually going to get some positive voltage. When it flips, we're going to get some negative voltage. When it flips again, we're going to get some positive voltage, negative voltage. So the sockets themselves actually give us alternating current. They give us voltages that sort of oscillate between positive and negative. That's really hard to use for my devices that expect a constant supply, a constant all positive or all negative voltage. So what we're going to do here is we're actually going to sort of mimic this diode design. Because the diode only lets charges through go in one direction, what I'm going to do is, how I create the electrical energy here, this one here is still constantly flipping back and forth at a frequency of 60 hertz. But what if I had a diode that's also hooked up in this circuit here? So what's going to happen here is, let's say for argument's sake here, the diode lets all the positive charges through. Because of the diode, this part here still gets through. When the otherwise battery would have been flipped the opposite way, when it's supposed to give me negative charges, it can't go through the diode because it's the wrong orientation. I'm going to get a zero charge for there. And then when it flips back, the battery goes back the opposite way here. We're going to then get a positive voltage here, and we will very quickly convert what would otherwise have been a sort of positive, negative, positive, negative, positive, negative. We're going to get a sort of a more constant supply. Sure, there's going to be little gaps in between. I'm sort of dramatizing a little bit because the frequency is so quick. These gaps here are not all that intense, and somehow we can just sort of sustain a positive voltage all the way through. There are other devices that we can add in. We can add in capacitors to temporarily store charge to not let this voltage really drop off to zero before the rectifier changes orientation and back to the positive voltage. So those are just two common devices here. They play around with, because of this depletion layer, there's a natural separation, there's a charge buildup, and the electrons can flow in this external circuit. Let's just do this top of the backside, and we'll leave the DSSC to the next lesson. By using this PN junction, this natural depletion layer, we can create a photovoltaic that converts light energy. So that's where the photo comes in to voltaic over to electrical energy. We're going to have already a forced separation. There's going to be already a junction set up here that doesn't let any net charges move anymore. But what we're going to end up doing is we're going to use solar energy, sunlight. And basically this sunlight here is going to promote even more electrons on an N-type semiconductor. it's going to give some of these positive holes here a little bit more kinetic energy. Again, we had said because of the depletion layer, the charges can't actually migrate through there. But because the solar energy is causing this net excess of electrons, I can allow some external circuit to allow the electrons to eventually make it to the p-type side, but not going through that junction. Whenever I have electrons flowing in one direction, that ends up producing my DC circuit, and we can put in whatever device I want on that wiring there. They just go and explain a little bit here in creating that depletion layer. This electron exchange can't continue indefinitely because there's a charge buildup, and basically this natural layer forms. In fact, for photovoltaic, it's not just going to be one PN junction. I can have PN junction, another one over here, another one over here. I can actually cascade my PN junctions and just hook up my wiring to allow the electrons to go where I actually want it to go. Let's just talk about just broad stroke here. What's the advantage of doing this? What's the disadvantage of doing this here? We talked about the sun being our unlimited energy supply. Right? It's running on fusion of hydrogen. It reduces our fossil fuel dependence, so we don't need to necessarily worry too much about, oh, I'm releasing a lot of carbon dioxide and a lot of other non-metal oxides causing environmental problems like acid rain. Because I'm less dependent on burning fossil fuels, I can actually utilize cleaner electrical energy. There's easier maintenance. I'm not having to do any enriching. I'm not having to do any separation, distillation of crude oil. I'm just purely taking sunlight, and I'm able to convert it into an electrical wired circuit to actually run my devices. However, you can imagine here, designing these as cascades here may provide some technological difficulties. We do definitely need sunlight exposure. So let's say in Vancouver here, we don't always get a lot of sunlight, especially in the winter times here. We need a way to concentrate the sunlight. We might need a way to store sunlight, but if I'm not having a lot of sunlight to begin with, it's going to be very hard. So you need to link it to some storage. So how can I trap all the electrical energy? It's only 10 to 20% efficient. If you compare it to gas power plants, those weren't 100% as well. The efficiencies were typically 40%, 50% or so, but a little bit better than solar energy. These photovoltaics, as we'll see in the next lesson, these solar panels will cover large areas which could have otherwise been used for other things. And also, in dealing with silicon here, we need to make sure it's pure enough. We need to make sure it's shiny enough so that it can actually absorb the solar radiation. That treatment is known to be very expensive as well. So I'm going to leave this lesson off here. Tomorrow we'll come back, we'll rehash a little bit of this photovoltaic, and then we'll look at how we can actually design a dye-sensitized solar cell that mimics exactly what photosynthesis happens inside a plant cell. So more on that tomorrow. Thanks, guys.